I designed on Altium Circuit Maker. This is the free version, of course, because I don't have a license to buy the actual full one. It doesn't include simulation, but I tried simulating most of it in Proteus because so I simulated in Proteus and I figured out it works, and then I built the PCB. So what we have here, let me just go to the schematic, is a magic wand, and it's not really a magic wand. It's basically just a wand where you can, here, if I go to 3D, it'll make it easier. So basically, when you turn on the device, each LED turns on, and then this one turns off, and then it goes in like a sequence: off, on, off, and then this one turns on. It's like a wand, like a sequence, like sequencing Christmas lights. Each LED is on one at a time, and then it goes in a line. So if we go back to our schematic, I can explain how this works. So over here we have our power source. 3 battery holders, each 1.5 volts. So when you put them in series, 3 times 1.5 is 4.5 volts. Over here we have our switch, and of course if it's in position 2, 3, it's an open circuit and electricity doesn't flow. Here we have our C2 capacitor, which is basically a capacitor that the rest of the system can pull from, so that it doesn't put too much strain on the battery every time the system needs a bit of power. And we can see over here it's polarized. Here's a positive side and here's a negative side. And then this power source leads directly into a 555 timer, which is our clocking circuit. I just copied the data sheet in terms of like VCC and where to put the capacitors and what values to have them at. Here's our potentiometers, and the potentiometers, based on their angle of rotation and their resistance value, it determines how fast the clock signal is outputted. So here's the modeling equations I pulled from the data sheet. So you can see here is the value of RA, which is our R resistor or potentiometer A, and potentiometer B, and then our capacitance. And then these are some other equations like the duty cycle and the period and the frequency. So the output of our clocking signal here on pin 3 out goes into a 4-bit counter. And here's our clocking signal for a 4-bit counter from the output of our clock. And basically this 4-bit counter counts from 000 to 2 to the power of 3, which is 8, so 111. I didn't really need the 4th output, so I didn't connect it to anything. But our A0, A1, and A2, and you can notice that this is a dual inline package of 2 4-bit counters, but I wasn't really using the second one, so I didn't connect it to anything. Anyway, you can see that our A0, A1, and A2 output go to a 3 to 8 LED decoder driver. So this maps 3 inputs to one of the 8 outputs. So let's say A0 is 1, and then A1 is 0, and then A2 is 0. Based on the data sheet, this would map to Y0, for example, and then the LED 1 would be turned on. And then on the next clock cycle, it would count to 010 instead of 001, and Y1 would be turned on, and this one would be turned off, and this one would be turned on. And then I create an array of LEDs that turn on once at a time sequentially. So once again, this is like our 3D view. Here are our 3 battery holders, and I made the PCB a rectangle, so it looks kind of like a wand. And here's our capacitor, here's a switch, here's our potentiometer A and our potentiometer B, some other capacitors, and our 8 LEDs and our resistors. So I think this is the 4-bit counter or the clock, and then this is the 3 to 8 LED decoder driver. Actually, I'd have to look at what U3, U2, and U1 are on the schematic. So this is our U2 is our 4-bit counter, U1 is our clock, and U3 is our 3 to 8 decoder driver. So yeah, this is my first PCB design that I designed with a clocking circuit, some LEDs, some resistors, power supply, and other resistive and passive components. Thank you for watching.